It solved your problem on Tuesday. By Wednesday, it forgot you ever existed. The window wasn't too small. The fix isn't a bigger one. Welcome to the Atlas. You shipped an agent that re-meets the same user every morning, and it isn't your prompt. It's a boundary nobody draws. Let's draw it. It feels like a memory problem. It's actually a physics problem. A bare model is stateless. Every run starts from a fresh window and throws away everything it computed the instant that run returns. There's no place inside the model for yesterday to live, so every run, it meets you for the first time. Inside a single run, the agent does hold things, the conversation so far, a scratch pad, the working context. But all of that lives in the window, and the window is gone the instant the run ends. Nothing carries to the next run on its own. Picture Dana, a customer you helped yesterday. She walks back in today, and the agent starts from zero, re-asking, re-diagnosing, throwing away everything it learned. In one 2026 report from Atlan, 83% of customers said they have to repeat themselves to multiple agents, and a third called it their single worst experience. Hold on to Dana. Whether the agent knows her tomorrow is the whole story. So where could yesterday possibly go to survive to today? Here's the line, and it's worth pinning down precisely since everything that follows lives on one side of it. There are two kinds of state, and they are not the same thing. One dies when the run ends. The other is built to survive it. The first kind is session state, what the agent holds during one run. The conversation so far, the scratch pad, the variables in play. It's real, it's useful, and it's gone the instant the run exits. That's a whole separate subject, its own episode, and we name it here only to draw the line. The second kind is persistent memory, and it runs the other way. Facts written out to an external store during one run, and read back into a separate later run. Same person, two kinds of state, one held inside the window, one that outlives it. So if a fact lives in the window, it's session state, and it dies on exit. If it survives to a future run, something wrote it down outside and read it back. This episode is only about that second kind, and the machinery that makes it work has 4 steps. The machinery that makes a fact survive has 4 steps, and once you see them, you can't unsee them in any memory system. Write, store, consolidate, retrieve, into a new run. Watch one fact ride all 4 across the exit. Step 1, write. During a run, a memory layer reads the conversation and pulls out the atomic facts worth keeping. Step 2, store. Those facts land in an external store tagged with who they belong to, a user id, a session id, so they can be found again. Step 3, consolidate. The raw pile gets distilled, duplicates merged, stale facts decayed, dead ones evicted because an agent that remembers everything remembers nothing useful. Step 4, retrieve. At the start of a separate, later run, the relevant memories get pulled back. By meaning, by keyword, by who they're about, and dropped into the fresh window before the model begins. That's the reversal completed. The model is still stateless. It still forgets on exit. The loop doesn't change that. It builds an external memory around the model, writing during the run, reading at the start of the next. The amnesia stays. The notebook survives. The step everyone skips is the third. Writing and retrieving are obvious. Consolidation keeps the store from rotting into a junk drawer. Skip it and retrieval rots the more you store. So, write, store, consolidate, retrieve. So what gets written into that notebook? Long-term memory isn't one undifferentiated blob. It comes in 3 kinds, and knowing which is how you decide what to keep. The first is episodic memory, specific past events. What happened, the action taken, the result. It's what lets an agent reason from precedent. Last time this customer had this symptom, here's what worked. The second is semantic memory, durable facts, preferences, domain rules, the stuff that's just true about Dana. The third is procedural memory, how to knowledge, the tool use patterns and workflows the agent has learned to run. The bridge between them is consolidation, that third loop step again. Take many episodes, find the pattern, distill it into one durable fact. Episodic is the diary, semantic is the fact sheet, procedural is the playbook. Most of what people mean by memory is semantic. But the powerful move is consolidating episodes into semantics, turning 100 conversations into one reliable thing the agent knows. It's Wednesday. Dana opens a new chat, a brand new run, a blank window, the model as stateless as ever. Last time, this is where it asked her to re-explain her whole setup. Watch what happens now that the notebook exists. Yesterday's run already did its part. It wrote her setup to the store, and then it exited, its window wiped clean. Today's run opens just as blank. But before the agent answers, the retrieve step fires. The memory layer queries the store for what's relevant to Dana, matching by meaning, by keyword, and by who the memory belongs to, and injects those facts into the window. So the agent's first line is, "Welcome back, Dana. Still on the EU region? Last time we indexed your slow query." Notice what happened. The model isn't remembering. It's being handed its memory at the start of the run, from a store that survived yesterday's exit. To Dana, it feels like it knows her. Mechanically, it read the notebook first. A fact written in one run, read back at the start of a separate one. 6 weeks pass. Dana migrates her stack from Postgres to MySQL, a normal Tuesday for her. She opens a chat. And the agent, recalling perfectly, confidently tells her she's on Postgres. It didn't forget. It remembered. The old truth, frozen. This is the consolidation problem made real. The agent logged every utterance and never reconciled them. So a fact that was true 6 weeks ago still sits there at full confidence, beating the new one in retrieval. The fix isn't to delete the old fact. Deleting loses the history you might need for an audit. The fix is recency wins, with invalidation. Write the new fact and mark the old one invalid, with a valid from and an invalid from stamp. The temporal knowledge graph engines, like Zep, do exactly this. Every fact carries a window of when it was true, so a stale fact gets retired instead of silently retained. Memory that only ever adds is memory that goes quietly wrong. A high relevance fact is accurate until the user's world changes. Then it's confidently dangerously stale. Lifecycle, not just storage. So what if the agent did its own housekeeping? There's a design borrowed straight from how an operating system manages memory, and it keeps 3 tiers. Core memory is a small set of facts always in the context window. Think RAM, fast, tiny, always loaded. Recall memory is searchable history that lives outside the window like a disk cache, not loaded, but one query away. Archival memory is an unbounded external store queried only on demand, like cold storage, huge, slow, fetched when needed. Here's the part that makes it self-managing. The agent edits its own core memory as it reasons, appending a new fact, replacing an outdated one. So it's constantly deciding what's worth keeping in the small, precious window and what can live further down the tiers. This is the RAM, cache, disk hierarchy applied to an agent's mind, and the agent is the one curating it. Not a batch job. The agent itself as it works. One open source design, Letta, is built exactly this way. Here's where it bites. The instinct, once memory works, is to remember more, store everything, keep it forever. That's exactly how memory turns from an asset into a liability. 5 failures and every one is predictable. 1. Unbounded growth routes retrieval. The more near duplicates you store, the more they crowd out the right answer in the top results. 2. Staleness and contradiction. Without lifecycle management, an old fact and a new one sit side by side at equal weight, exactly like Dana's 2 databases. 3. Wrong memory retrieval. Even perfectly accurate memory hurts if it surfaces the wrong user, the wrong account, the wrong case, and cross-session identity breaks under anonymous, multi-device, mixed login traffic. 4. Poisoning. Memory is an attack surface. An adversary who can slip records in can steer what the agent recalls. In testing on one agent, a few poisoned records came to dominate retrieval. 5. Privacy. An explicit memory store is personal data, so the right to be forgotten and the right to correction apply, and they collide with the audit trails regulators expect. None of these is exotic. They're the default behavior of a store that only grows. Storage without governance is a liability with an interface. Governance can read like bureaucracy. It's 4 concrete controls, and each one neutralizes a specific failure you saw. Control 1, invalidate. Give every fact a life cycle, a valid from and an invalid from. So when the world changes, the old fact is retired, not silent and kept. That's the Dana fix, generalized. Control 2, scope. Retrieve by more than raw similarity, by meaning, by keyword, and by exactly whose memory it is, so you never pull the wrong person's record. Control 3, consolidate and evict. Keep merging duplicates and dropping dead facts, so the index stays sharp and growth doesn't rot retrieval. Control 4, audit and honor deletion. Treat the store as personal data. Keep a trail of what's there and where it came from. That both satisfies the right to be forgotten and defends against poisoning by provenance. 4 controls, 5 failures handled. The store is the easy part. The governance is the product. An amnesiac model wrapped in a notebook that survives the exit and stays honest. Everything we covered on one board, the model is stateless, so a bigger window isn't memory. The boundary, session state dies on exit, persistent memory survives it. The loop, write, store, consolidate, retrieve into a new run, keeping episodic, semantic, and procedural facts. The proof. Dana recalled across the exit, staleness fixed by invalidating, not deleting. The bounds. Govern it. Invalidate, scope, evict, honor deletion. The model forgets by design. The notebook is what survives. That's persistent agent memory end to end. The model forgets by design. The notebook is what survives. If this made it click, subscribe to AI Tech Book. Next up, once it survives, how do you make the right memory surface, governing it, and ranking what comes back?